From the expression of the energy in the Ising model, we are going to derive the energy in the so-called mean field theory. Mean field theory. This is actually an assumption, so we will assume that we will get good results, quote-unquote good results, because we are going to approximate the expression for the energy in the following way. We are going to replace the generic value for the spin, Si, with the average value of the magnetization, M. Is this legitimate? Well, the answer is not quite. It will give us some crude results because the approximation is very strong. But the qualitative behavior that we will see in phase transitions will be quite accurate. With this kind of approximation, the energy becomes, this is equal to minus B times capital N, the total number of points in the lattice. Remember that we have a lattice in D dimensions. Then here we have M minus J. And then when we replace M, here we get M squared. Remember that this summation should be interpreted in the following way. So the index I ranges over all the points in the lattice, whereas the index j, if we fix I for a moment, for example, let's assume that I takes this value here, then j can take either this value, or this value, or this value. So in two dimensions, the possible values that j can take for each I is 4. In d dimensions will be simply twice the dimension, 2d, because in two dimensions we have 2 times 2, so 4. But in d dimensions, in general, we get 2d. And then we have to multiply this by n, but we also have to divide by 2, because when we span across all the points in the lattice, we are really counting the pairs twice, because, for example, when we consider this I, we can have either this pair, this pair, this pair, this pair. But then if I, for example, were equal to this point here, then we would also count this pair. But I mean, this is just twice the pair that we counted earlier. And in general, this is done for every point. So there is an overcounting, and in order to take care of that overcounting, we have to divide by 2. So basically here we just get d times n. But it is just convenient to rewrite this summation by defining another parameter, q, to be equal to 2 times t. So basically here we can rewrite this expression like this. So we can divide by n, so the energy can be divided by n, and this would be equal to minus b times m minus 1/2 j, and then we have q m squared. Now let's assume that we have a configuration of spins such that we have n up spins, so we have n times plus 1, and then we have n down spins. So the total number, of course, would be equal to capital N, and the average value for the magnetization would be n up times plus 1, which is the up spin, and then we have plus n down times minus 1, which is the down spin, divided by capital N. This can also be written like this, 2n up minus n over n, by using this expression here. So we can also write n down as n minus n up, and if you substitute it there, this is what you get. Now, the number of configurations, of such configurations, that we call omega, well, it's quite easy to understand. This is just n choose n up, or if you want, this is equal to n choose n down, and this binomial coefficient is just n factorial divided by n up factorial, n minus n up factorial. Of course, this is just n down factorial. So you can see the symmetry in this kind of binomial coefficient. So this one is equal to this. Now, if we use Stirling's approximation, since n is very large, we can approximate n factorial, and in general, all these factorials like this. This is n to the power n, and then we would have e to the minus n. If we replace this expression together with the expression for n up factorial and this factorial here, you put it there, you can also rewrite the natural logarithm of omega in the following way. It is n natural log n minus n up natural log n up, and then you have minus n up natural log of n minus n up, like this. Now, since we know that m, the average magnetization, is equal to 2n up minus n over n, we can also rewrite this in the following way. So n up can be written in terms of the magnetization as n plus 1 times n over 2. And similarly, you can write n minus n up as n times 1 minus n over 2. Now we can substitute these expressions there, and by means of some simple algebra, you can write the natural log of omega divided by capital N, which is approximately the natural log of 2 minus 1/2 1 plus m natural log of 1 plus m, and then you have minus 1/2 1 minus m natural log of 1 minus m, like this. Now, in our mean field approximation, the effective free energy that we have already defined in the previous lecture will give rise to the following. E to the minus beta times capital F of m. Remember that this is equal to the summation over the spins Si given a certain magnetization m, e to the minus beta E of Si. Now we are going to replace, in place of Si, we are going to put m. So we are going to consider the average value, and therefore here we are going to write e to the minus beta E of m. And then we have to sum over all such configurations, but the number of configurations is simply omega. So here we are going to get omega times e to the minus beta E of m. You can see that omega depends on m from this expression here. And remember that we also defined the effective free energy per unit spin. So this was also defined as lowercase f of m times n. And therefore, from here, from this expression, if you take the natural log on both sides, you can write f of m approximately equal to minus b, the magnetic field, times m, minus 1/2 jqm squared, and then you have minus T, the temperature, and this is just the inverse of this beta here. So then you will also have the natural logarithm of omega that will come from this expression when we take the natural log of both sides. So the natural log of omega can be written from here, and therefore you can write natural log of 2 minus 1/2 1 plus m natural log of 1 plus m, and then you have minus 1/2 1 minus m times natural log of 1 minus m. And we know that when we have the expression for f of m, we are interested in the derivative of f with respect to m, and we set it equal to 0 because we want to find the minimum value for m so that we can approximate the partition function. And if you take the derivative of this expression, what you get is basically the following result. You have beta, which is just the inverse of the temperature, because remember that we have set the Boltzmann constant equal to 1. So we have beta times the magnetic field plus jqm equal to 1/2 the natural log of 1 plus m over 1 minus m. Now, this function here can be shown that this is equal to the inverse hyperbolic tangent of m, and this is quite simple because, let me do it. If we define y to be the hyperbolic tangent of x, we know that the hyperbolic tangent is the ratio between the hyperbolic sine and the hyperbolic cosine. So this is equal to e to the x minus e to the minus x divided by e to the x plus e to the minus x. Now, if you invert this expression, in particular, you first multiply by this, so you get y times e to the x plus e to the minus x equal to e to the x minus e to the minus x. You can multiply this expression here by e to the x, so you get y times e to the 2x plus 1 equal to e to the 2x minus 1, and you solve this equation for e to the 2x. And once you solve it for e to the 2x, you can take the natural logarithm in order to find x with respect to y. And if you do that, what you get is x equal to 1/2 natural logarithm of 1 plus y divided by 1 minus y. But now we have written x with respect to y, and we know that y is the hyperbolic tangent of x. So basically what we have found is the hyperbolic tangent inverse of y. So this equation here can also be recast in the following form. M is equal to the hyperbolic tangent of beta times b plus beta jqm. And this equation is quite famous, quite well known for the Ising model. There is a nice intuition behind this equation here. In particular, this can be derived by assuming that each spin experiences an effective magnetic field given by Bf, the effective magnetic field, equal to B plus JQM, which includes an extra contribution here from the spins around each specific spin that we are considering. In this way, the interactions in the Ising model have been replaced by an averaged effective field. And this is sometimes called the mean field, and it gives its name to this technique. In the next video, we will start discussing how phase transitions occur in the Ising model.